Welcome to the Clear to Send podcast, a podcast about wireless engineering, where we educate you on Wi-Fi technology, talk about design tips, troubleshooting, interviews, and the tools. Here are your hosts, Roel and Francois.
Hi guys, welcome to a brand new episode of the Clear to Send podcast. This is Francois, your host, and I'm here this morning with Roel. Hey Roel, how are you?
Hello, good morning.
And today we're going to talk about antenna, right? We're going to go a little bit deeper into what an antenna is and how it works. And to do that with us, we have Ben Robson, which he loves antennas. He's like day in and out working on antennas. So he's going to come in and help us to understand how everything works. And we're going to try to relate it to the antennas we use in the Wi-Fi world and on our Wi-Fi installations. So Ben, good morning. Thank you for being here with us. Would you mind introducing yourself, just telling us a little bit more about you and where you're from and why you love antenna so much?
Yeah, good morning, everyone. My name's Ben. I'm from Ashford in the United Kingdom. I've been a sort of RF engineer professionally for about 12 years now, and so I've developed propagation models and designed a couple of antennas.
And the story behind Ben being on the show is he was actually one of my students for one of the EKO class, and he started to giving us small sessions on antenna design and so on. So
nice.
And then he gave us links to study that we'll put in the show notes if you guys are interested.
So
links to learn a little bit more about how antenna works and the physics behind it.
Okay, so the student became
so I
the
thought
teacher.
It would be a good idea to have him on the show.
Awesome.
All right, so on this episode we'll do I guess an introduction of how the antenna works, because you could spend hours talking about these things, especially if you go deep into the physics. But I guess for this first episode, we'll just, try to stay high level a little bit. And the first thing we want to talk about is how an antenna will radiate the energy, how the power is delivered to the antenna. So talk a little bit about the cable, the RF cable, and then we'll talk about things like a reflection coefficient, Vswr, and hopefully it makes sense. After we start to talk about that. After that, we wanted to talk about, the dipole and explain, how the dipole behave in the free space. Talking about the impedance, the radiation resistance, the radiation pattern. We're more, I guess, familiar with radiation patterns as Wi-Fi guys. Then we wanted to talk about the impedance, and that's when it relates to the radiation pattern. Then we wanted to talk about the different propagation mechanisms, behaviors, so reflection, diffraction, absorption, conductive ground. Then we wanted to talk about the difference between the different frequencies, right? 900 megahertz, 2.45 gigahertz, 60 gigahertz. What does it mean for the propagation of the signal? Then we wanted to talk about link budget. What's important to consider when you do a link budget. Before meeting Ben, I thought it was pretty straightforward. After seeing his link budget, I was like, okay, there's a little bit more involved in it. And then we wanted to close the episode talking about, what does all this mean for Wi-Fi design, right? Does improving the accuracy of RF models improve the Wi-Fi design? So we'll close talking about that. So Ben, let's start by talking about how the antenna radiates energy, and I'll let you drive how you want to answer that energy and where you want to start.
Okay. Well, just a quick refresher on, because I'm going to be talking a lot about dBs here.
Yeah.
So just a quick refresher on that. And dBs is always used in RF, mainly because it's nice and easy to handle, because you just have to add and subtract dBs to get your final answer. Whereas if you, because all it is a ratio, like a power ratio. and normally you do it's against 1 milliwatt. So it's how much power compared to 1 milliwatt, and that's what we would call a dBm. So we can use dB scale as a measure of power, dBs on their own as a measure of loss, and we also be talking about dBIs, which is instead of relative to power, it's relative to an isotropic antenna, but we'll come on to that. So the key notes to know about dBs is every 10 is a factor of 10, and then every 30 is a factor of 1,000, and then you can half is 3 dBs. So you can then combine those elements together to quickly work out what that really means. So we'll move on to actually how do we get power to the antenna in the first place. And we normally use coaxial cable, which has a center conductor inside of it, usually with surrounded by a dielectric, which is usually just Teflon or PTFE, and then an outer ground element of it. If you are looking to buy RF cable, you'll see there is a huge amount of choice of all these different types of cable. The two main differences that you want to be aware of, first of all, is 50 ohm cable and 75 ohm cable. In Wi-Fi and sort of higher frequency, we tend to use 50 ohm cable as pretty much the standard for across the board. So that's the impedance of the cable. I'll get to a bit what that means as well.
Yeah, I was going to say that's the impedance, and you find that information on the antenna spec sheet, I believe, as well.
Yes, yeah. So because the cables are 50 ohm impedance, most antennas will be designed to match that 50 ohms, or try to. And again, we'll get onto that. I just want to talk about the sort of cost of cables as well. So you can buy, with cables, you will have an associated loss to them, and that loss increases every meter. And this is something you'll see on the spec sheets as well. It could say 0.1 dBs loss per meter, or higher, or sometimes they do it in feet, or 100 feet, or 100 meters. But you can just divide it down to the actual length you want to use. So there's no complicated maths to work that out. You can, if it says it's 2 dBs per meter, then if you've got 10 meters, it's 20 dBs of loss. But that loss will also be frequency dependent, and the rule of thumb is the higher the frequency is, the more loss there is in the cable, because it has everything in RF is relative to the frequency you're using, and the wavelength of that frequency. So if you imagine a 1 meter cable and your wavelength is 10 centimeters, the wave travels 10 wavelengths along that cable. But now if the wavelength is 5 centimeters, it has to travel 20 wavelengths to get to the end.
So more loss?
Yeah, so you can effectively double the loss. That's not always the case with cables. You have to check the spec sheets, but that's generally what happens. And the main reason for that extra loss at higher frequencies is something called skin depth, which is, we're getting pretty into the physics already. But the way the current is distributed inside that center conductor of the cable, the current sort of groups around the outside of that cylinder, if you like.
Mm.
And as you get higher and higher in frequency, that depth that it's concentrated gets smaller and smaller. And what that effectively means is as you go up in higher frequency, the cross-sectional area of your cable is decreasing, which means it's becoming more resistive, essentially.
Mm.
So that's why you get higher frequencies is more lossy, because it's the length, and the cross-sectional area has got smaller. So if you buy higher, really low loss at high frequencies, you'll tend to see that the cables are a lot thicker, and because they're thicker, they're a lot stiffer. So that's definitely a consideration if you trying to install it. It's the trade-off between that low loss performance and the flexibility.
Yeah, I've seen the only application of long RF cable I've seen in the field for Wi-Fi use was in warehouses where they would put the access point somewhere, and then they will have like coax cable to install the antenna maybe under the ceiling, and you would have long RF cables. I mean, for all the deployment I've worked on, I try to place the antenna where the AP is, and I would have like a 1 meter RF cable, right?
Yeah. The shorter the better, really, because if you use shorter cables, you can get away with cheaper cables. That's the other thing is, if you want low loss, it comes at a cost.
And it would be probably cheaper to hire cablers to run a cable wherever you want the AP is, rather than buying the expensive RF cable with low loss.
Yeah,
I think. Yeah.
I mean, as long as you can, like I say, if you're going too long, like tens of meters, then you're going to get quite a lot of loss in a real cheap cable.
Yeah, and you gave us some calculators that you can actually calculate that yourself, and you can play with the different cables that they, I think it's from like specific cable manufacturers. They let you calculate the loss depending on the length, and so you can choose a particular cable that they sell, and then you can select the frequency, and you can select the length, and then they're gonna tell you it's gonna be 4, 6, 10 dB loss for that specific length, and you can plan that into your link budget.
That's right.
So do you want to talk about VSWR?
Yeah. So you've got a cable now, and you want to send an RF signal down it. And so RF is an electromagnetic signal, or electromagnetic wave, and essentially all it is alternating current, but at much higher frequency. So like alternating current at home, you've got 240 volt mains AC, and the AC, well, in the UK is at 50 hertz, and that's actually a wavelength of 6,000 kilometers. So it's pretty big wavelength, really. I think that's I think that's getting close to like the radius of Earth.
Yeah, I think it's 65. Yeah, you're right.
Yeah. So yes, and all that, I say that alternating current is the same we're getting at the Wi-Fi frequencies, but obviously it's oscillating a lot faster. Thousands and thousands of times faster.
Yeah, we are a billion You're talking about 2.4 gigahertz and 5 gigahertz?
Yeah, so yeah, a billion times faster for 2.4. Yeah.
Yeah.
Yep. And as the frequency increases, the wavelength decreases. So it's so at 2.4 gigahertz, the wavelength is now 12.5 centimeters.
Yeah, and this is why the higher the frequency, the less it propagates through any kind of material.
Yes, yeah. So that, like I say, that wavelength is really crucial in everything RF, really. We'll get onto a bit of how that affects the propagation and even your antenna design, and the cable losses we just mentioned. So when you terminate a cable with a load, and the load normally in this scenario we're going to use is just an antenna. Now, if you attach two cables together, they have the same impedance. Well, providing you've brought two 50 ohm cables, and as the impedance is exactly the same, that means that all of the energy you've put into that cable will be transferred into the second cable, because it's a perfect impedance match. Now, if the impedance is mismatched, which will always be the case with an antenna, because it's very difficult to design an antenna with a perfect match, and so you're always going to have some energy reflected back. A good analogy of this is light going through different mediums. So I don't know if you remember back at your sort of school physics lessons where you've got light, let's say going into, let's go into water, let's say, going into water. So and remember in light, the refractive index is the key factor there, isn't it? So if light is traveling perpendicular to the water and the refractive index is the same as air that it's already in, then all the light will travel through as if there's nothing there. But when air meets water, water's got a different refractive index than air. So some light is reflected back off the surface, and then some of that light travels into the water. And the same thing happens with RF, because after all, RF is light is a electromagnetic wave as well. And you can, rather than the refractive index, you can think of it as different impedances, and you'll get exactly the same result. If you look up Snell's law, which is how much energy is transmitted through different mediums when they meet, so if you change the angle that you what's the word? If you change the angle that the light is coming from, you'll get more reflection and less transmission into the media, and that's the same with RF as well. So back to the cable. If you've got a 50 ohm cable and your antenna isn't 50 ohm, there will be a mismatch, and so some energy will be reflected back down the cable to the transmitter, and with a good sort of transmitter design, you can sort of cope with that reflected energy coming back. And the way VSWR comes into it, so VSWR stands for a voltage standing wave ratio, which is a bit more in depth in the physics. So you have a a standing wave inside the transmission line. But I don't tend to like to visualize that. It's a bit more complicated to get your head around, I think. And it's the ratio of like the peaks of the voltages, essentially, of the incident wave and the reflected. The easiest way to interpret VSWR, which you'll see on a lot of spec sheets, is actually return loss. And that's so much more easy to understand, and I always, and it's easier to visualize, and most antenna designers will design to a return loss rather than a VSWR.
Yeah, and then you can calculate the VSWR, right? Once you have the return loss, it's like you have a mathematical formula.
That's right. So the VSWR, the return loss, and the reflection coefficient, they're all related. So if you know one, you can calculate the others, no problem. It's just sort of a different way of representing the same information, really. But return loss I think, is the easiest way to understand.
Yeah, I agree with you.
So I'll give you a quick example. So if I've got my transmitter, and ignoring cable loss at the minute, if I've got a transmitter and I'm sending 30 dBm, so that's 1 watt, and my antenna has 10 dBs return loss, which is 2:1 VSWR. Well, roughly. That means that I'm trying to put 30 dBm into the antenna, but 10 dBs will be reflected back. So what that means is I put 1 watt in, but and 20 dBms will be returned back. So that's 0.1 watts or 100 milliwatts returned, and then the rest of that energy is gone into the antenna.
So you're saying that if you have a VSWR of 2:1, it means 30% of the energy is reflected back onto the cable?
I don't know what it is in a percentage.
Oh, you said 10 versus 30, so I'm guessing it's 1/3, right?
No, because it's dBs. So.
Oh yeah, you're right. Oh.
It's 100 times less is reflected.
Okay, 100 times less.
No, sorry, 10 times less reflected.
So 1/10 of the energy?
1/10, yep.
Okay. So 1/10 of the energy is reflected back onto the cable. And this is the example you took of 2/1 is typically what you will see on a Wi-Fi antenna. I did some quick check this morning, and this is what you'll see on external antennas.
Yeah, so that's a pretty standard like design goal for an antenna is if you've got 2:1 VSWR or a return loss of 10 or better, you can say that that's well matched in terms of antennas.
And that depends on the frequency. I think you mentioned it, but that depends on the frequency. You're going to have like a frequency at which the antenna is like the most efficient.
Yes.
Yeah. And I guess we'll talk about that after.
Yeah. So that, I guess we'll go with that when we go into antennas a bit, but that will come up. Yeah.
And then, sometimes what you'll see on spec sheets is they'll give you the VSWR. They'll tell you it's 2:1, or sometimes they'll tell you it's equal or inferior to 2:1. I've seen that as well. And sometimes they'll give it to you depending on the band. So they'll tell you for 2.4, it's 1.6/1, and on 5 gigahertz it's 2:1.
Yeah.
And so going back to the discussion around the reflected power versus VSWR. I think for us, it would be easier to understand that, 1/10 of the energy is reflected back versus 2 to 1.
Exactly. Yeah.
Yeah, but they don't always show us that information, right? They just, I guess, but
Yeah.
we can. Fortunately, there's a calculator you can use, and you just put the VSWR, and then they tell you what the
Return losses. Yeah.
the return losses, which is,
Yeah, I guess if you're just looking at the data sheet, then you would see that value and go, "What do I do with that?" Like,
yeah, exactly, exactly.
Yeah. Yeah. So if I'm looking at a data sheet and I see, 1.6 to 1, I'd say that's so that's 13 dBs return loss. So I'd say that's quite well matched. But then that value is only for one frequency, and they've picked that value for the whole band. So it may be the way they've designed it that across the band it does meet. It's always meets that, which you can design in.
okay.
They never go in. Some manufacturers are better than others, and they will actually. Sometimes they'll show you a
graph,
a plot. Yeah.
Yeah,
they'll call it.
There'll be some visual to it sometimes, but if I take that number, like let's say like this antenna, the Cisco 2513 P4M antenna, you look at a data sheet and it says VSWR for each band. If I just take 1.6, for example, do I just plug, that's the number I plug into a VSWR return loss calculator to calculate? And then there'll be like this output, which then tells you the VSWR that you put in. And it's, I guess the big one is the return loss, which actually says 12.74 dB.
Yeah.
Okay.
Like I say, that I would find that easy to visualize more than anything.
Okay.
And they have the plot we're going to talk about, Ben, is the S11 or S11. I'm not sure how they pronounce that.
S11 it is.
S11, yeah. And so pretty much what this is the graph that shows you how much power is reflected from the antenna, but across your frequency space.
That's correct. Yeah.
And so usually what happens, what I've seen, correct me if I'm wrong, but you will have like a dip at one point, which means that's where, the antenna will have the better match, so less loss. And then they'll find a threshold somehow, and then they'll say anything that's between those 2 points, those two thresholds, will be below, let's say, 1.6 VSWR or below 2 to 1 VSWR, and that's what they will consider being the effective, operation of the antenna.
Yeah. So when you design an antenna, if you look at that, well, first of all, that S11, if you're interested, is a scattering matrix reference. It's how they describe, if you take a measurements of a 2-port system, you use scattering parameters to define each port. And in this scenario with a 2-port system, you have S11, which is I'm putting energy in and what's being reflected back. But you can also measure at the other end, which will be S21. So it's the energy going from port 1 to port 2. The notation is backwards. So if you see S21, that's port 1 to port 2. It's just the way the mathematicians use it. So.
Yeah, and we'll put a link in the show notes because you sent me a link that explains that really well from a website called Antenna Theory.
Yeah. Oh, yeah, that's quite a good website, actually.
That's really good. Antenna-theory.com is a really good,
a
good website to learn about antennas.
Yeah, then they have a couple of links to some good YouTube videos as well, explaining a bit more sort of visually how the physics works, which is quite nice. Yeah, so the S11 graph, like you said before, you have that dip. So it's like if you're looking at it, it'd be like a straight line at the top, and usually if you were displaying return loss, that is, usually it's 0 at the top, and then you get a straight line around about 0, then a V shape, and then back up to 0. And so that at that point of the V, that's where the antenna is most resonant, if you like, and where we get that closest to the 50 ohm match as well. And how wide that V can get, if you like, is the impedance bandwidth of the antenna.
Yeah.
So if you have that V really, quite shallow, or so it's like it's coming out at 45 degrees, let's say. That would be a really wide impedance bandwidth. So you can design an antenna with wide bandwidths, and so when you see on the spec sheet 2:1 for the 2.4 band, the 2.4 band is actually quite easy to achieve that bandwidth because it's only 100 megahertz at 2.4 gigahertz. So
yeah,
that's actually quite easy to achieve, and so that 2.1 can quite easily be across that whole frequency range. And that's why you'll see, like you say, on that Cisco antenna, that they've split up the 5 gigahertz bands because it's almost a whole gigahertz that you've got to cover in the 5 gig band. So to get an antenna with bandwidth across that frequency range is a lot more challenging. So that's why they've obviously got one band where they can achieve better matching than another band.
So in terms of antenna design, does it mean that you're going to have more elements to make sure that you can, operate on a larger bandwidth? Like I'm thinking about 6 gigahertz and the fact that they have 1200 megahertz of spectrum. Like, is it going to be complex to design antenna then for 6 gigahertz?
Yeah. So when you get to the sort of broadband antenna theory, that there's lots of different techniques and methods of getting that extra bandwidth. So you can have, like I say, extra elements, or you can have something which is called parasitic elements, which are they're like bits of metal that aren't actually even connected to the antenna, but they're close to it. There's just a huge array of techniques you can do to increase that bandwidth. But there's always, as with any design, there's always trade-offs. So maybe you can get the bandwidth, but your return loss is getting higher and
greater.
Yeah. So or you can get the bandwidth, but now the antenna is massive.
Yeah, you cannot put it in the phone.
Yeah. Yeah. So there's always trade-offs. It's definitely a real challenge to get antennas that work and put them into a phone. I think that's quite incredible that they get it to work, really.
Yeah, I'm impressed as well. Like when you learn more and more about it, it's like it becomes an art. It's kind of like Wi-Fi design.
Oh, it definitely is. Yeah, black magic they call it.
Black magic.
Yeah.
So one question I'm interested in sometimes if you look at those S11 graph, you'll see two dips. So this, I would guess, this would mean the antenna is like a dual band antenna type of thing.
Yes.
Does it mean that it's different, like in the design? Like, is it like one piece of equipment, or is it different equipment that you put together so you can, you can
No.
transmit on
So
different frequencies?
that would just be that one antenna.
Okay.
But it will have, like you say, different elements on it, or sticking out, or different bits cut out of it, and
Okay.
to achieve those two dips. And actually, if you look at that graph, but on a much larger spectrum, so you looked at, 3 or 4 times the spectrum on the graph, those dips will actually repeat over frequency as you get more resonances further up you go.
Okay. All right. So that's talk about the reflection coefficient and all of that. Then what happened when the energy travels through the cable, gets into the antenna, so some of it is reflected back. Now, how is that energy, like at the antenna level, how is that energy radiated into the air?
Okay, yeah. This leads into the dipole, really, which is one of the simplest antennas to build, and where a lot of the electromagnetic theory is based on as well.
Okay.
So if you imagine, so we've got this alternating current going down our transmission line, and then if you were to splay open that transition line at the end and make 2 points perpendicular to the transmission line, so you've got like a T shape at the end now, and one part of that is the center conductor going up, and the ground bit of the coax cable is coming down, and the alternating current is going along the transmission line and then sort of bending round along the antenna, if you like.
Okay.
And because it's alternating, so you have it's going like in a positive direction on the one that's connected to the center feed, if you like. So the one going up is, the current is going up at one instance, but at the same time, on that one that's connected to the shield on the ground, the current is also going in the same direction. So you've got like a doubling of current in the same direction. And then as it's an alternating current, so that's just one instance in time, this goes back to Maxwell's equations, which is extremely daunting to look at if you're like what the hell is this? if you look it up, you like the sort of mathematics behind it. But essentially what he says is, he has is Maxwell's equations, like four different laws, if you like, so that I'll just tell you what they are. So the first one is an electric field is produced by a time-varying magnetic field. The second one is a magnetic field is produced by a time-varying electric field or a time-varying current. And third one is electric field lines may either start or end on charges, or are continuous. And magnetic field line, the final one is magnetic field lines are continuous. We don't really need to know for this talk much detail about that, but the key one there was a magnetic field is produced by a time varying current, which is our AC signal. So having an alternating current generates a magnetic field, and because a magnetic field is generated, an electric field is generated.
Mhm.
And then because the electric field is generated, a magnetic field is generated. And it's like perpetual, if you like.
Yeah.
So we've got this alternating current up and down this dipole, which is making this magnetic. If you look on top of the dipole, so how to explain that for the podcast?
Yeah.
Is it
So
like looking at
if you hold a pen
down?
in your hand, and make a T shape with the pen, with your index finger and thumb holding it in the middle. Yeah.
Yeah.
And then if you look down the end of the pen, so the pen is perpendicular to your eyes now. So that's like the top view of the dipole. So magnetic field lines will circle the dipole antenna.
Okay.
From that view.
So that's what that's what the dipole is, an omnidirectional antenna.
Well, it's an electromagnetic field, so it's the electric and the magnetic, if you like.
Okay.
It's that's a bit of a tricky one to explain, but it's the electric field that we're really interested in. And the electric field, if you then turn your pen so it's now parallel to your eyesight, so the pen's going up and down, the E field will come out as parallel lines, if you like, to that pen. And that's really what we're interested in, is those parallel E fields.
Okay.
So it's very complicated to try and get in your head. So
we can include some images.
An electric field coming out that's parallel to the dipole antenna.
Mm-hmm.
And as that moves out in space, it's varying in amplitude, like a sine wave, if you like. But then connected to that E field is also the magnetic field, which is perpendicular to it.
Okay.
Which will increase and decrease in amplitude the same way the electric field does. Am I making sense?
Yeah, it's definitely hard to describe over an audio podcast, but sometimes I view it as like taking a donut and just putting that looking at it where you stick a pen and have that pen go through the donut hole. And then I look at the signal like that, or like an apple, and you're like
Yeah, so that's the sort of that's the radiation pattern of the antenna. So when we talk about an isotropic antenna, that's like a point source in free space, and energy radiates from it equally in every direction. So essentially it will radiate it in a perfect sphere, if you like.
Yeah, 360 degrees.
Yep. But obviously we can't make a point source in reality because we need to have an antenna of some sort. So the dipole is the nearest we can get to that.
Okay.
But obviously you've got your long pen, and the E field radiates nicely, like I said, parallel to that. But not much energy, if anything, comes out the end or the point of the pen.
Yeah, the very tip of that pen. If you look at that like of an antenna, there's not much actually coming out, propagating through that top point.
That's right. Yeah. I'll just quickly, and so that's how you may hear as well about antenna polarization?
Yeah.
Yeah.
So again, that's if you look at the dipole. So if you've got it the pen sticking up vertically, and it's pretty much as simple as this. That's vertically polarized because the E field is vertical. And now if you stick the pen parallel to the ground, it's horizontally polarized. So the dipole is quite easy to see what the polarization is. It can get more complicated to explain in more complex antennas, but.
And I think you have videos that explain that on the Antenna Theory website.
Yes, yeah. There's lots of good information on there, really.
Yeah, they explain the A field and the magnetic field, and they show you like some sort of 3D visualization so you can, understand that.
Yeah.
So the polarization will impact the propagation then.
It will impact the propagation, but it will also impact how well you receive it as well. So on a simple radio scenario, if you're just using dipoles, you want your transmitter to be vertically polarized and your receiver to be vertically polarized. If they're not, then you'll receive significantly less power, essentially.
Which is hard in the real life because if I take my phone, for instance, I might be using my phone on the table when it's just laying down on the table, but I might also be using my phone, vertically. So yes. I might be impacting my, my signal by just changing how I use the phone. But like you can't really, like a phone is a phone. People use it different ways.
Yeah. So what you would try to do is design an antenna that is what we call cross-polarized. So it can use both polarizations.
Okay.
But yeah, it when you get into the details, I think it makes it a lot more impressive that that Wi-Fi works and your phone works.
Yeah. It's like, how is this thing still working?
Yeah. Yeah.
But could it be that if you do have it on, let's say, Francois, you're talking about your phone on the table versus holding it up maybe to your ear, would that different polarization really affect the Wi-Fi signal for that device dramatically?
I think if I don't think we really need to worry too much about polarization at this stage. But what is interesting to point out is what affects our perfect donut radiation pattern.
Okay.
And the answer is pretty much everything. Just from an antenna point of view, the length of that dipole, the thickness of the cable you use, or if the antenna is bent in some way, or pretty much everything you can think of will change, have an impact on that radiation pattern. And also, not only the radiation patterns, the impedance of the antenna as well. For example, if you have your dipole and you've designed it to match a half wavelength dipole to match your transmission line, your coax cable, and then you now put that antenna in surrounded by plastic, that will change the impedance of the antenna. So you would have to design your antenna knowing that it's going to be surrounded by plastic. You see what I mean? And like what type of plastic are you going to use? All the different plastics have different properties.
Yeah, how it's going to affect eventually the propagation of that signal. And so as Wi-Fi professionals, when we're dealing with these antennas, is that something that we should look at? Should we look at the build of the antenna? I mean, most of the time I just see an antenna, but I don't really expect or inspect the way it was built and what components were used to build it. Typically that stuff I'm not really concerned about, but I do trust the data sheets quite a bit.
Yeah, I mean, it's sort of, you could spend ages optimizing your antennas and spend a lot of money doing so. But if you don't optimize them and it still works anyway, you know, what are you spending all that money for? But I guess we're going to talk a bit about that towards the end, but I don't really know. I don't think you're going to. It's good to have an appreciation, I think, of what affects your radiation pattern. So it's things like placing your access points in a building. You know, if you put it inside a cupboard or behind a ceiling, or you know, you're just
near HVAC,
adding more things that's affecting that radiation pattern.
Yeah, exactly. And I see your point there, because you're spending like $1,000 on an access point only to install it improperly, which affects how the signal is propagated out into the open. So you're already messing up, I guess, how the antenna is designed to work. You've now manipulated that signal, and maybe it was done, you know, not maliciously. Like maybe somebody deployed it, they didn't know, they don't understand the radiation pattern. But I guess when we talk about all of these things, there's so many components to it because of physics that we have to take into consideration, right? We've got you talked about the Vswr, the type of cables that you would select, especially if you're, I know I deploy access points, but antennas that may be farther away from the access point. So I use like a directional antenna. So there's things like impedance that I have to take into consideration, basically the loss that I would have. And I guess some of the things that I think about is, all right, if I'm going to place my antenna about 4 feet away from my access point, if I haven't calculated what type of loss I would have with that cable, how does that affect the radiation pattern?
So if you've got more loss in the cable, you're just less energy is being transmitted, and it's just as simple as that, really.
So it's whatever if we go back to what we've learned in like CWNA, for example. So if I've set the transmit power of the AP, would a system, a WLAN system, be able to tell the loss and give you the more accurate EIRP based on that loss? Or is it just, here's your transmit power, but you don't actually know that you've created a loss because you've either selected the wrong cable or you just have some sort of loss there between the AP and antenna?
Yeah, it's one thing I've found in the Wi-Fi world is it's very difficult to make good measurements like that, if you like, in the real world, because just on the transmitter side of things, like the variation in output power can be, you know, a few dBs. So whenever I set the output power on my access point, you know, I take that with a pinch of salt. Like I think it's all right, it's going to be higher or slightly lower than maximum, or I don't say that as that's exactly how much it says it's going to give me. I mean, it's a good guess, but I don't. It's just not that accurate, really.
Okay.
And again, like if you are playing around with that transmit power, I think if you are doing like external antennas and you've got the spec sheet that says, right, this is the gain of my antenna, but again, that gain is like the maximum gain in one direction.
Yeah.
We usually don't get that details, right? They're just giving us the gain. So I guess we assume this is, what I've assumed is, let's say you get an external antenna that has cable attached to it. I'm guessing the gain is taking into consideration the loss of the cable.
I would say no.
Okay.
Well, normally, when you antenna specs, that's just the gain of the antenna, and that is it.
Yeah, that's true.
So that's when you see the dBi, which is, so how many extra dBs am I getting compared to
antenna,
an isotropic antenna?
Mm. Okay.
And then so you'd add, so for your link budget, you'd go, this is my cable loss that I've calculated at 2.4 gigahertz. This is my gain that I've got from the spec sheet at 2.4, and then you can adjust your access point power level.
It's interesting.
Sure you meet the regulations.
That's interesting because I've never calculated a link budget indoors, and when you talk about antennas the way that you're talking about them, it makes me want to actually calculate a link budget, because am I thinking I'm getting, the power I'm getting out of the antenna? Because if you've got the loss there, and I think this is more particular for antennas, and maybe correct me if I'm wrong, antennas that you're using a cable to attach to the AP, and not necessarily so much about like a dipole antenna that connects directly to the connector. Like, are we going to see would we see significant loss if we're using like a dipole antenna connected directly?
You won't see significant amount of loss, no. I mean, like I say, it's that how many times has that wavelength had to travel to get to your antenna? That's what you've got to think about. So if
I was going to ask, what about the, because we don't really talk about that when the antennas are inside the AP, because they're like connected to the circuit board directly.
Yeah.
But sometimes we have small cables, right?
Yeah. Yeah. The small, like if you're talking like a couple of centimeters or whatever, I mean,
yeah,
you don't need to worry about that really.
Okay.
The loss is going to be.
So generally, at what length should somebody be considering some sort of link budget, or the type of cable they're using? Are we talking like 4 feet, or I don't know how to convert that to metric, but
I would say
like one.
I'd say probably a meter.
Yeah,
or 3 feet. Once you're getting over those sort of distances, then
you should really consider
picking a different
cable
can make quite a difference.
Okay. That's very, I think that's actually really good information for people to know, because it might not seem like a big distance, right? A lot of the antennas that we buy that do have the cables attached to them, they're already there, but we don't ever consider, or I don't think it comes across many people's minds about, all right, how much loss am I getting through this cable? Because you might be designing the Wi-Fi network specifically, right? You might say, all right, here's the transmit power that I'm going to use, but then you might forget about EIRP. But when you look at that EIRP number, it's probably not calculating the cable loss, because there is no cable loss value that I put into my design software, which I'm using Ekahau. I've never seen that value, unless I just haven't seen it, but I don't think that's something that we consider a lot.
Yeah, I think I don't know how often you guys would use external antennas though with long cables. So
Yeah,
I guess
it's pretty rare in Wi-Fi.
Yeah, not that often. I'm usually using the cables that are attached to the antenna already. I maybe extended the cable once or twice, but I did know about the VSWR, but I asked for the help from the vendor in selecting the right cable so we don't hit a large amount of loss.
Yeah. So definitely on the 5 gigahertz band, and when you're going more than a meter, I'd say, it could be a couple of dBs difference really, just on different cables.
So now let's talk about the propagation through the free space, right? The electromagnetic waves traveling through the free space, and I guess we can talk about. You had a couple of elements here. You had conductive ground, reflection, diffraction, absorption. I'm familiar with reflection, diffraction, absorption. Conductive ground, not so much. Would you be able to just explain what these are and how they could affect, the signal?
Yeah. So I'll talk a bit about the free space loss quickly. So we talked about the isotropic antenna that was radiating in all directions in a spherical shape with equal amounts of power. So if you extrapolate that out, so that sphere is getting bigger and bigger and bigger. If you then look at one point on that sphere, you can see as the radius increases, the amount of energy is also decreasing because it's like blowing up a balloon almost. So you've started with the same amount of energy at this one point, and as the balloon gets bigger and bigger, that energy is getting spread over a bigger area. So it's getting thinner and thinner, if you like. And that's what's happening in the free space model. It's like a spreading loss almost. So the energy is just getting spread out. And that's what Ekahau uses in its modeling, which is at 2.4 gigahertz and 5 gigahertz. That's quite a good model to use for indoors for those sort of fairly close distances. Now, normally, the thing about electromagnetic waves is anything that's conductive or highly conductive is effectively like a mirror. So a wave will just reflect off it. So one model that you quite use outdoors is something called the plane earth loss model. And by plane earth, that means that the ground is perfectly flat and a perfect electrical conductor.
The Earth? Are you saying the Earth is flat?
Yes.
I knew it.
It's a good approximation for short distances, but because then you don't have to consider the radius of the Earth. But I think from about 10 kilometers or more, you need to start thinking about the radius of the Earth. But for hundreds of meters, an assumption that the Earth is flat is acceptable.
Yeah, and with the reflection in an office environment, that just becomes multipath to us. But as signal is reflected from an antenna, I mean, you're going to get some sort of loss from that. But it's something to consider in the, I know in the Bay Area, like there's a lot of interesting offices, so the reflection is pretty high.
Yeah. I'll just explain a bit more about that conductive ground. And so on the simple scenario where you've got two antennas on a flat field and you've got a perfectly conducting ground, so all the energy is reflected off the ground. You'll have now two rays at your receive antenna. You'll have the direct ray and an indirect ray that's reflected off the ground. And when an electromagnetic wave is reflected, you get a phase inversion. We haven't really talked about phase, but that's probably something for another day. But what that means is the reflecting signal received at the same time, at the receiver, is received in antiphase. So you get this sort of cancelling effect. So you essentially get even more loss from your propagation scenario by having a reflecting surface.
Okay. So
but,
it's pretty much distracting the original signal.
Yes, but in the real world, all the surfaces aren't perfect electric conductors. So
yeah,
you'll get if you ever see a propagation plot, you'll see all these sort of big fast dips and
yeah, you're right.
And that's what that is. It's those waves being received in antiphase, and you get these huge nulls.
Okay. And does that because does it then? I'm just thinking it matters, like the floor, the material used for the floor would matter then, right? If you're in a warehouse and have like a concrete floor, that might be reflecting the signal way more than if you're just in a carpeted environment.
Yeah.
Okay.
It will make a difference, but again, it's that sort of adding that extra layer of complexity. Is it helping you to design the Wi-Fi?
Yeah, it would still work.
Yeah. But it's interesting to know that basically anything metal will be reflecting or adding to that diffraction as well. And the Ekahau software doesn't take into account reflection or diffraction.
Yeah, no, not at all.
That's what we call ray tracing.
I believe IBWave does consider both.
Yes, I think it does. Yeah. And then there's, when you get into it, there's lots of different diffraction models you can use to try and speed the calculations up as well, and they have varying accuracies.
And these would matter more if you're designing for longer distances?
Yes, it's definitely more longer distances. Perhaps if you were doing, like a point-to-point bridge between buildings or something like that, you may want to look at using a different propagation model.
Okay.
But the way Akahau, because they just use it as everything absorbs it, so everything has an attenuation, and that works reasonably well as well. Again, the differences in the different frequencies. So if I say, so we've got 900 megahertz, which is 33 centimeters wave. Is that right? No, 0.3 meters. wavelength. Yeah, so 33 centimeters. Then 2.4 gigahertz is 12.5 centimeters. 5 gigahertz, okay, 5.8 centimeters. And then 60 gigahertz, we're looking at 5 millimeters for the wavelength.
Such huge differences in wavelengths, and it's something a normal person just wouldn't even consider. And when I started working with Wi-Fi, learning about these different frequencies and the wavelengths, I was like, what? And I remember learning this from Keith. I think Keith Parsons. I think he had some good diagrams that showed the differences in the wavelengths. I believe that's where I saw it from.
Yes, it's like I said before, it's knowing the wavelengths is actually a really useful way to look at the frequency, because from like a loss perspective. So again, same with that in the propagation, like open. The same with the cable loss. Like if you've got 100 meters and your wavelength is 5 millimeters, it's got a lot of wavelengths to get to the other end. So your loss is massively increased. So you're looking at a terminology used in, I'm not sure if they use it in the Wi-Fi, but cell size.
Yeah.
So it's definitely used in the mobile cellular sort of world. So as you go up in frequency, your cell boundaries, if you like, shrink.
Yeah, it's much smaller.
Yeah. No, that's because, like I say, at 5 millimeters, it's got to go a hell of a long way to get somewhere.
Yeah,
and also you have the wavelength will impact the size of the antenna as well.
Yes, yeah. So if you imagine a half wavelength dipole, which is, you can imagine how the size of that dipole massively changes with frequency. And that's an interesting point as well, that as your antenna size decreases, so does the objects in the environment that frequency will interact with. So if you've got like metal rods or I don't know, you've got a door and it just happens to have 12.5 centimeter bits of metal in it, your 2.4 gigahertz is going to more strongly interact with that because it's at the right length.
Oh, that's kind of interesting. Okay.
So that's how they design shield?
Yeah, so if you like a Faraday cage,
okay.
If it's a cage, you've still got apertures in the cage, haven't you?
Yeah.
So if it's like if you use chicken wire, let's say, that will only be effective up to a certain frequency, and then the wavelengths will be small enough to
go through
ignore the mesh.
So that's why people use foil.
Yeah. Well, like in a microwave, you can, the mesh on the microwave door is really small, isn't it?
Yeah, it's very small.
Yeah, very.
And then that blocks 2.4 gigahertz.
Although some of those can go bad over time. I mean, if you got the spectrum analyzer, you could see that.
Yeah.
And that's how we changed our microwave in the workplace. When we got a spectrum analyzer, we were playing with it, and we kept seeing the signal on 2.4, and we realized it was the microwave, and we thought it was too strong because we were in our office. We were kind of close to the kitchen, but to see it that strong, we ended up having somebody replace it with a more industrial type of microwave because it was used so often.
Yeah, what usually fails is the seal around the door, actually. So to open and close the door, you need a conductive seal around it.
Oh, okay. So just don't get a cheap microwave then.
Yeah.
You can just change the door and fix the problem.
Yeah, or maybe just clean the seal.
Or clean seal.
Yeah.
Oh, so if we talk about 60 gigahertz, right? So then that kind of explain the range of it, right? The small range of it.
Yeah, exactly. Yeah, such a small wavelength.
Yeah, and why you need a line of sight for the signal, because I was working with 70 gigahertz a couple of years back, and anything like a leaf, something tiny, could just kill the signal. Even rain or whatever the weather is in that environment, you want to take into consideration.
Yeah, well, rain is something that's been heavily studied for satellite communication systems. So they've even performed studies to work out what is the average size of a raindrop and things like that.
Wow.
To work out, I think it's about 2 millimeters or something.
Okay, now I got to look up the research for that.
Yeah.
And also in 6 gigahertz, I think you have the oxygens, something like it starts to resonate with oxygen, right?
Yeah. So the water molecules and oxygen, molecules. You get different resonances as you go high up in frequency. But again, you think of those resonances again relative to that wavelength. So anything that's around half a wavelength, so 2.5 millimeters, it's just going to interact with that. So if you've got raindrops that are 2 millimeters, which is I think probably quite reasonable, it's just going to absorb all of that energy.
So you can understand, like, heavy rain will pretty much affect your wireless link if it's 60 gigahertz.
Yeah, so in SATCOMs, when they do their link budgets, they have something called rain fade that they factor in.
I remember using a calculator that asked me which part of the world I'm in, and it had an average of what that rain fade looks like, and so that gets added to your formula.
Yeah, yes, and they base their link budgets on like a percentage of uptime, if you like. So how many times of the year will my link drop because of rain?
Yeah, and I remember when I did deploy the 70 gigahertz link, it wasn't a far link. I think it was less than a mile or about a mile, and we had heavy rain, I think, a couple weeks later, and I knew the rain was coming, and so I remember looking at what the signal was and then having to monitor it afterwards to see if there was any kind of loss. I didn't really see much, so there probably wasn't a big storm where that link was, but I was hoping to see something.
Yeah.
So I was going to say that's if we talk about very high frequencies, right? What they call the millimeter wave.
Yeah,
that's right. Yeah,
signals. Yeah, and they're starting to talk more about that because in the 5G they are thinking of using some of those higher frequencies.
Yeah. I think the 5G is quite interesting because it seems to me that there's all these different technologies now competing for the same spectrum.
Yeah.
And I think it's just like who's going to win.
Who has more money?
Yeah.
I mean, if you go with the lower frequencies, comparing 60 gigahertz to 5 gigahertz or even now 6 gigahertz, it's that 6 gigahertz will propagate farther. So you don't need, I guess, the larger, more expensive equipment that you would usually use with like 60, 70 gigahertz and having those distance limitations associated with the higher frequencies.
Yeah. I mean, some of the research ideas for the 60 gigahertz are quite interesting. So they're talking about like having because your cell size is so small, you can have a really good frequency reuse plan. So you can almost, I know one paper I looked at, they were saying like having like an access point per person on an aeroplane or something.
Like on the same channel?
Not on the same channel, but like because
is it kind of like an array?
Because it attenuates so quickly, you can like 10 people, a few people away, you can be on the same channel again.
Yeah.
Okay. So then knowing these propagation differences, how does that play into the link budgets? Because earlier you mentioned like the shape, the curvature of the Earth, reflection. We talked about antennas and using cables indoors to APs. So there's a link budget there as well. How does that affect things like for a Wi-Fi person like SNR and what we could expect from a device receiving that signal from an antenna?
Yeah. So the sort of basic link budget is the Friis transmission equation. That's FRIIS transmission equation, and that's just simply power transmitted minus the cable loss plus the gain of my antenna minus the path loss plus the receive gain antenna minus cable loss, and then your received power. So that's the sort of basis of all link budgets, really.
Yep.
And what you can do, and certainly when you look at satellite links, they really go into a lot of detail because, they're so far away. I mean, geostationary's it's like 36,000 kilometers away.
Yeah, and they got to deal with the rotation of the Earth and weather.
Well, geostationary, so they're okay.
What kind of station?
Geostationary.
Oh, geostation.
Yeah, so you have to be that far out so that you're always above the same point in Earth.
Gotcha.
The low Earth orbit ones, they're the ones that spin around. But yeah, like the sort of things they have to deal with there, they've put a lot of detail into their link budgets to make sure that they can guarantee that service. So from building from that Friis transmission equation, so you've got your received power, but then you've also got a noise level in your receiver. You've got receiver noise, and noise is usually generated from resistive elements in the system, and also sort of thermal noise, so depending on the temperature of it as well. It's quite a complex field to get into, but essentially you have a noise floor, and as you increase your receiver bandwidth, you also increase the noise floor. So if you double your receiver bandwidth, the noise floor will increase by 3 dBs as well.
Yeah, we're familiar with that.
So if you take your receiving signal, and let's say it's 10 dBs above the noise floor, we can say that that's a signal to noise ratio of 10 dBs. And the reason why that is important is when we've got our signal and we start to modulate information onto that signal, certain different modulation techniques will require different signal to noise ratios. I think it's an easy example to understand that is just amplitude modulation. So amplitude modulation, all you're doing is, if we do amplitude shift keying, it's an easy one to explain. All that's doing is you've set, let's say, 4 different discrete amplitudes, and each different amplitude represents, as we've got 4, can represent 2 bits. So a 1, or so we've got, like, the highest amplitude could be 1 1, next one down could be 0 1, then 1 0, and then 0 0. Now your signal to noise ratio to receive those different amplitudes will be dictated by your lowest amplitude level there. So if that lowest amplitude will need to be above the noise floor, if you like, to get all 4 different discrete points received correctly. So and as you get more and more complex modulation schemes, so you're adding in more and more discrete amplitudes, you can see how you're going to need more and more signal to noise ratio to cope with those different amplitude points.
Yeah, because we haven't really talked a lot about the receive sensitivity of the other end, which it's going to be about the devices. We always talk about the signal coming out of the AP or the antenna, but when it becomes a receive signal, as you do this link budget, you've calculated all this, the cable loss and path loss, also the SNR required to hit those points, right? That's going to affect things, other factors as well. I mean, there's so many numbers involved. It's kind of crazy how Wi-Fi seems to work pretty well, even when you don't do these calculations. But
yeah, well, there's some parts of Wi-Fi, like the 160 megahertz channel in AC. I did a link budget for that, and in sort of an optimistic scenario, I could, from my link budget, I could see that it would only work for, I think it was like 8 meters maximum.
Yeah, see, if we do these calculations, we would be able to see that and then plan accordingly with that. But with AC, we just don't have enough channel reuse. So then there's other factors to consider, right? You're now having channel overlap and all of that. But it does come back to, in the end, when we work with Wi-Fi, about knowing all these antenna details and these measurements. It always comes back to providing that experience for the end user and their device that they're using. But how does that?
So that the antennas in the devices are going to be wildly different between devices, and even like how you hold your phone or how you hold the laptop, or if you've got if everyone's using laptops, is there, or no, a good example I suppose is if everyone's got like desktop towers,
right?
But they've got metal desks, for example, and they put they've got their Wi-Fi card on the back of their tower.
Yeah, in the very back, up against the wall of their desk. Yeah. But
I think it helps, like knowing all of this helps us take better decisions when it comes to antenna installation, right?
Yeah.
And appreciate the fact that they work better. I guess they won't work better, but their operation would be optimized if we install them, clear of any, metal or of any direct surface, I guess.
Yeah.
And also, like you said, on the client side, we can also take that into consideration. Like you mentioned the tower computer, under a metal desk, but like in the field, we've seen it, really expensive pieces of equipment, let's say in hospitals, and then to connect to the Wi-Fi, they have like a very cheap Wi-Fi adapter that's inside the equipment, right? That's obviously made out of metal, right?
Yeah.
So all of this is clearly going to impact the way this device works on the Wi-Fi, and sometimes just the fact of maybe taking that into consideration in the design of the equipment, or having some sort of rubber antenna that sticking outside of the equipment will improve the way this device will see the signal,
Yeah.
significantly improve it.
And I think you actually touched upon a good point, Francois. Like, this is the last part that I want to talk about, is when we have these vendors making these antennas, and for example, you brought up the one with putting it in a metal enclosure or something. How should we interpret or validate that these antennas are working correctly? Is it worth trying to test if an antenna says it's got a 60-degree beam width? Should I try to verify that and verify the components are working? So that way we can improve the accuracy of what we're doing in Wi-Fi network designs? Like, is that something we should consider doing, or is that just too much effort?
I think that could be too much effort, but the key thing, especially if you're using something that says it's a directional antenna, the key thing to know is what direction that it's supposed to be looking at, really.
So as long as we point it in looking at the data sheet, knowing what the propagation is of that antenna, but not basically what we've mentioned earlier in this podcast is that some of these components are not perfect, right? It's just like end user devices. They're not, if I have my iPhone's not going to be the same as the other person's iPhone. We'll see that the signal received is going to be different from what I'm receiving if they're right next to each other.
Even at Cisco, like, they're providing these data sheets for their antennas, but how well are they even testing them? How much money are they putting into antenna testing, or are they just simulating it in a model and go, yeah, that's good enough, and send it off?
Yeah, in their little contained lab.
Even when you simulate an antenna, it's still just a model. It's not exactly what it is in the real world.
Right. And then there's also the manufacturing process. So something could happen there. Just different components being used. And so I think it could be done. It could be done if you want to spend the time verifying every single antenna. I think the point in which I would test it is if I'm seeing pretty drastic results where I validated everything else up until the actual antenna, and then maybe just swapping out the antenna to see if that resolves it. But I haven't gone to the point where I am trying to test every element of that antenna to verify the operation of it. Because I do feel like it would be, just in my case, too much effort. I don't have that much free time to verify. If it doesn't work for me, then I'll just swap it out.
I mean, I think just doing your site survey, I mean, that's essentially verifying that the antenna is working, really.
Yeah, that's true. It is. It could be part of it. Because if you're meeting the requirements, then yeah, it's all working correctly, right?
Yeah. So when you're doing your site survey, you're sort of taking the whole system into account, really.
Exactly.
But obviously, on the client side, you're doing the survey for one client, if you like. I think that's an important thing to remember as well.
Okay. Yeah. I thought it was a lot of great information that you've added into this episode, because it's details that we haven't really considered when deploying. I know I don't look too much into some of these details. The only time I ever really look at VSWR is when I'm trying to extend the length of the distance between an antenna and an AP. I think talking about impedance and resistance is something that we all should know. I mean, it's talked about in the CWNA, and then talking about the different characteristics of electromagnetic waves and how different environments can affect that signal right now. So we talked a lot about different things, very technical. It's kind of hard to really talk about these topics on an audio podcast. So we'll include some visualization, some links and resources in the show notes, because I think that's going to be even more critical if you want to fully understand this topic, get down to like the nitty gritty. I mean, we won't necessarily have your knowledge, Ben, but we really do appreciate you coming here onto the show to talk about antennas.
Yeah, no problem at all. Yeah, I think you're right. A visual aid really does help. That's the big problem with RF is it's invisible.
Yeah, exactly.
Yeah.
All right. Well, I know this is probably one of our longest episodes, but I thought it was really good detail to learn again the how antennas work as we relate it to Wi-Fi. Ben, thank you for joining us here on the show. Do you have a blog or something, or Twitter you want to share with people if they want to engage with you more?
I'm actually not on any social media.
Okay, that's good. That's actually really good.
Yeah,
you get to focus on antennas. That's the point. But we want to thank you for joining us on the show, sharing your knowledge. So we'll definitely add all these links into the show notes. And Francois, thank you for organizing this.
Thank you, Ben. Thank you, Roa. No problem.
All right. So if you guys want to see the show notes, go to cleardescend.net/223. That's where we'll have them. And again, thank you for sticking with us on this long episode. But I think this is going to be one I'll re-listen to get more understanding. So thanks again, and we'll see you guys in the next episode.